So primary and secondary unbalanced forces. The inertia force due to reciprocating parts are force required to accelerate the reciprocating parts. So F1 is equal to Fr is equal to mass into acceleration, that is m into omega square into r into cos theta plus cos 2 theta by n. We have discussed in the previous article that the horizontal component of the force exerted on the crankshaft bearing is equal and opposite to the inertia force. This force is an unbalanced one and is denoted by F suffix u. So F specify the force use the unbalanced force. So F suffix u is equal to m omega square into r cos theta plus cos 2 theta by n is equal to m omega square r cos theta plus omega square into r cos 2 theta by n is equal to Fp plus Fs. Fp specifies the primary force, Fs specifies the secondary force. So the expression m into omega square r cos theta is known as primary unbalanced force, and m into omega square r into cos 2 theta by n is called secondary unbalanced force. The primary unbalanced force F suffix p is equal to m omega square r cos theta. The secondary unbalanced force F suffix s is equal to m omega square r into cos 2 theta by n. So we have to note certain things. The primary unbalanced force is minimum when theta is equal to 0 degree or 180 degree. Then the primary force is maximum twice in one revolution of the crank. The maximum primary unbalanced force given by Fp into max is equal to m omega square r. The secondary unbalanced force is maximum when theta is equal to 0 degree, 90 degree, 180 degree and 360 degree. The secondary any force is maximum 4 times in one revolution of the crank. Maximum secondary unbalanced forces is given by F suffix s is equal to m into omega square into r by n. From the above, we see that secondary unbalanced forces is 1 by n times the maximum primary unbalanced forces. In case of moderate speeds, the secondary unbalanced forces is so small that it may be neglected and compared to primary unbalanced force. The unbalanced force due to reciprocating masses varies in magnitude but constant in direction, while due to the revolving masses, the unbalanced force is constant in magnitude but varies in directions and all. Partial balancing of locomotives. The locomotives usually have two cylinders with cranks placed at right angles to each other in order to have uniformity in turning moment diagram. The two-cylinder locomotives may be classified as inside cylinder locomotive, outside cylinder locomotive. So inside cylinder locomotive and outside cylinder locomotive. Then partial balancing of locomotives. The locomotives, the two cylinders are placed in between the planes of two driving wheels as shown, whereas the outside cylinder of a locomotive The two cylinders are placed outside the driving wheels, one on each side of the driving wheel as shown. So, partial balancing of locomotives. The locomotives may be single or uncoupled locomotives and coupled locomotives. A single or uncoupled locomotive is one in which the effort is transmitted to one pair of wheels only, whereas in coupled locomotives the driving wheels are connected to the leading and trailing wheel by an outside coupling rod. The effect of partial balancing of reciprocating parts of two cylinders. So, variation in tractive force along the line of stroke. The variational in tractive force along the line of stroke, swaying couple and hammer blow. So, variation of tractive force. The resultant unbalanced force, so due to the cylinders along the line of stroke, is known as tractive force. So F suffix T is equal to F is the force, T is the tractive force. So that is equal to 1 minus C into M omega square into R cos theta minus sin theta. Maximum and minimum value of the tractive forces are the variation in the tractive is equal to plus or minus root of 2 into 1 minus C into M omega square R.